Hello. Okay, it's loud. All right. Thank you for the introduction. And hello, everyone. Welcome to my talk, Maintainable Python Deployments at Scale, Decoupling Build from Runtime. So in this presentation, we're going to talk about how we can make our Python deployments more scalable and maintainable by using Python tooling instead of relying exclusively on Docker. So I've already been introduced, so I'm not going to cover the details on this slide, but my contact information is there on the bottom right. So if you have any questions afterwards, feel free to reach out to me. And I'll show these details again at the end of the presentation, so you don't have to copy my email right now if you don't want to. Okay, so today I'll explain the hidden costs of deploying Python code, the problem that shows up when we pack everything into a single Docker image. When we bundle everything into a Docker image, we're usually combining 3 separate layers of deployment. And I'll make a case to open up other ways of thinking about how we deploy Python code. And after I explain the problem and the proposed solution, I'll cover 2 types of strategies and examples of how they can be used to scale Python deployments. The first one will be using cached Python virtual environments. And the second one will be deploying packaged Python applications that follow the PEP 441 standard. All right, so let's start talking about the problem, the hidden cost of Python deployment. Today, when we are deploying Python code, most applications rely on using Docker for deployments. And so a quick reminder of how Docker works. We use Docker to package our deployments into a single file that is portable across systems. And we do that by writing a Docker file. It defines how we want to create a Docker image. Then we run a command, and the Docker image is created. And the Docker image is used to create one or many Docker containers that run our application. And it makes deployment very simple because we only have to work with just one file that gets invoked every time we need the application to run, and we have good reproducibility. Okay, so let's give an example for how a classic Docker deployment type of workflow works. Let's say that I'm working on a brand new project, and I wrote this simple Python application here on the right. Very straightforward. You import some packages, you do some stuff with it, and you print hello PyCon Taiwan. Very straightforward. And let's say that I've been running and testing it locally, and it works great. Now I want to deploy this into some kind of production system so it's not just running on my local computer. The most standard approach is to bundle the application that I had on the previous slide as a Docker image and deploy it as a Docker container. So this code here on the right is a very simple example of a Docker file that's used to generate a Docker image. I define the base image, I install some system dependencies, I run pip to install packages for Python, I copy my code over and I run my code. Very straightforward. Then after this, I run the Docker build command separately to turn this into a Docker image. And this entire setup is pretty boilerplate. In fact, if you ask AI to help you deploy your Python code, this is very likely the type of result that it's going to suggest for you on how to deploy your application. So once the Docker build process finishes, your application is bundled as an immutable Docker image. And it's very straightforward and gives me a lot of confidence that whatever was created will more or less deploy properly. And this process works very well, and there's nothing wrong with it. If you sit me down today and tell me to write a Python service, this is probably the process that I'm going to do. However, what works in isolation doesn't always work at scale. So patterns that work for 1 to 5 developers in a small organization might not work in an organization where you have multiple teams, different people, different applications. So now you're probably thinking, well, what's the problem with this? Docker images are immutable. So if you want to make any changes, you will need to create a new Docker image. So to highlight, we have this one Docker image, and we can deploy it, and it works perfectly. Tomorrow, I want to make an update to my Python code. Now we have 2 Docker images. Now your team is going to build some more Python applications, each with their own Docker image. And you realize that you have to update every single image for its system dependencies due to maybe a security vulnerability. Great. Now you want to install and update some additional Python libraries, and you want to fix some bugs in your code. Okay. So other teams will then take your they'll take your team's application and take that Docker file and they'll inherit from it and build more Docker images on top of it. And at some point, you accumulate so many different images across your organization that it becomes a nightmare. And we often call this a Docker sprawl. So at this point, you're required to update maybe your organization's Python version from 3.12 to 3.13. How do you even know where to start? Everything's kind of hidden inside of a Docker image, and you have so many of them. So by using this default pattern, you run into a few issues where you have to rebuild a Docker image for any kind of change. One's in your Python code, the Python packages that they use, or any system changes. And the number of Docker images becomes so bloated as more images are built that it becomes really difficult to keep track of them, especially when they start inheriting from each other and you start having circular dependencies where Docker images will inherit from one another. And if you're trying to streamline operations, such as patching a security vulnerability, it becomes extremely complicated operationally to address this. So the core problem is that building a Docker image for every change can create maintainability and scalability challenges. So great, we've defined the problem. And my goal here is not to tell you to get rid of Docker, but to explain how we can still use Docker, but allow our applications to be more flexible and fluid. So to do that, we need to first understand how we can decouple the different layers that go into a Docker image. Then we can manage them properly. So let's break down what goes into a deployment. When we deploy code, there are 3 layers. There's the system dependencies. These can include packages such as urllib, your GCC version, things that you often associate with Linux packages. The second one is Python dependencies. These could be things like Boto3, Flask, Pandas. These are things you often associate when you run pip install to install a Python package. And the third one is application code. These are essentially a custom logic that you're writing to build out your application and often associated as your .py files. So great, we've defined the 3 layers. What do these layers look like in an actual Docker file? Okay, so this is the Docker file from earlier on in our presentation. And I want to revisit this to clearly show what the 3 layers are and where they are in this Docker file. So they're all tightly coupled here, and here they are. So in the first layer, you have your system dependencies, which include your base Docker image and your system packages. The second one, you have the pip install that has your Python dependencies. And the last one, you have your custom Python application logic, where you copy your Python files over and you tell Docker how to run it. So you can see that in this default type of Docker deployment setup, we're bundling these together into a single Docker file. And that is why we are so inflexible with how we manage our applications. So this here is the main concept of my presentation. Not everything needs to live in your Docker image. System dependencies can go in the image, and your Python code and the Python packages can stay outside. This means that we can manage our deployments without having to rebuild a Docker image for every single change that we make. For things that change more frequently in our Python application, we can deploy those changes without having to rebuild and create more Docker images. So we've essentially decoupled the Python dependencies and the custom code on the right outside of the Docker image on the left, which has your system dependencies. So this is the main point of the presentation, and let's talk a little bit more for what this might look like. So here again is the original Docker file, the same one we've been looking at. And again, it has all 3 deployment layers coupled into the resulting image. And let's decouple the Python dependencies and Python application out of this resulting Docker image like I showed in the previous diagram. Okay, this might look a little complicated, but don't worry, I'll cover what it's doing. So rather than having the Python dependencies and application built inside the Docker file itself, we put these in a script that can dynamically run different Python code based on the project file environment variable. So the script on the right is essentially taking the responsibility of that, and it will dynamically download a zip file, unpack it, and then run the Python requirements during runtime to install them, and then run the Python application. So this change is a straightforward example to show how we can split our deployment into a Docker file and a dynamic script. And the Docker image will no longer be responsible for all three deployment layers. Instead, the Python dependency and the Python application are managed separately from the Docker context. So anytime we need to make changes to our Python code, we can just put down the zip file and set it up so that it references the zip file, and we don't need to touch anything on the left with the Docker file. So this approach scales better in a complex organization. We manage one Docker image that provides a consistent environment for our Python application. If anything needs to be updated, we have the flexibility to address it in the appropriate layer. And this solves a lot of our operational problems that we mentioned earlier. So in this diagram, you have one Docker image, just one, that runs with your system dependencies, and you have multiple zips of your Python dependencies and your Python packages responsible for each application. Great, so the problems I mentioned earlier are more or less solved. We no longer have to rebuild for any change, rebuild a Docker image for every change, and we no longer have this Docker image sprawl, and our overhead for deployments have become a lot more straightforward. And this is great. We solved the original problem that we proposed. However, engineering is about trade-offs. So with this example that I put up on the screen, 2 slides ago, with this example of that new Docker file that was split into a deployment script, we now have increased startup latency, and we have increased complexity of managing the Python applications. So increased startup latency would be attributed to how we run pip install to install our Python dependencies at runtime. In the original Docker solution, we run pip install once, and the dependencies are baked into this Docker image. So we don't have to install this every single time the application runs. We just do it once. And by running pip install at this file like I have on the right, we are deferring this to run at runtime. So every single time a Docker container boots up, we are now running pip install. In large organizations with large requirements.txt files, this can take several minutes. And I've actually seen organizations that kind of did something similar, and it would take 12 to 15 minutes every single time a Docker container came up with that image. So organizations with horizontally scaling infrastructure would have a difficult time accepting this increased startup latency with this proposal that I made. The second trade-off is that we now have more complex management of Python applications. With the Docker-based solution, we are running the code inside the Docker containers environment. And by storing your Python application as a zip somewhere, you're essentially managing additional complexity of managing the zip files. And we run into issues where the code that's in the zip file may not run appropriately on a different system. And so the good news to this is that there are solutions to address these two trade-offs. And I will go into real-world examples to address how we can solve these two types of problems. But before I do that, I want to do a quick summary on everything that has been discussed so far. So the standard pattern for deploying Python code results in your application being bundled as an immutable Docker image. And the problem with that is that building a Docker image for every change can create maintainability and scalability challenges. And to address this, we can approach deployment with a different perspective. Not everything needs to live in your Docker image. And so my proposal is that we can use Docker to manage our system dependencies, and Python dependencies and Python code are managed externally. Okay, now we are going to cover real-world examples that also address those two trade-offs that I mentioned earlier for startup performance and deployment complexity. Okay, so let's discuss this first strategy, caching virtual environments. So this approach can solve for the long startup times due to installing your Python dependencies at runtime. So that would be when we run pip install every time the Docker container comes up. This is intended to address that. So if you're working with Python, you've likely created virtual environments before. And if you haven't, that's okay, but I'll talk a little bit about how virtual environments work at a high level. But when you use it, you run this command, venv, that's built into Python. And when you run this, it creates a virtual environment for you. And by using a virtual environment, you keep your Python dependencies isolated from other contexts, from your system complex, from the application you're running. So you can create multiple virtual environments on a system when you want to juggle different applications or different workflows that you have on your computer. So an isolated Python environment means that you can run pip install, and it will install your Python packages into a virtual environment. And if you need to set up another Python environment due to cleaner isolation requirements, package conflicts, changing your Python context to that of another project, you can just create or load another virtual environment. And what you may not have realized is that a virtual environment, what you may not have realized is that a virtual environment is just a directory. When you use a virtual environment and you run pip install to install a package, all it does is that it takes the installation process and it just installs everything into the directory that was created for a virtual environment. And because it's a directory, it means we can just cache it. So again, this might look like a lot of code, but I'll explain, so don't worry. On the left, we create a virtual environment, and it installs Python packages, and we zip it. On the right, we create a separate context. So the right side is, you can imagine it's a different environment from the left side. So the right side, we take the same zip files as created on the one on the left. We unzip it, and we activate the virtual environment. And if you run something like pip list after you activate it, you'll find that you'll have the same exact packages that you had when you installed them on the left. And so in most cases, if you just download a zip and you show the packages, they're there. This runs a lot more quickly than if you're running pip install and actually installing the packages on demand. So this way, you don't have to wait for your Python dependencies to install. You can just use a cached version of the virtual environment. There's one condition to this. The environments must be the same. So you can't run the context on the left on your laptop and then run the context on the right and expect it to work flawlessly. There may be issues with portability in that regard. So this is an example of an architecture to handle caching the virtual environment the way I kind of talked about in the previous slide. So the top left defines the requirements.txt file, which is typically how you would define your Python dependency in an application. And the bottom left shows a file cache of zips of different virtual environments keyed off of the hash of the requirements.txt file's contents. And the right side shows the Docker container that runs a script that does a write-through cache. So how this works is that we have a Python requirements.txt file on the top left. We run the MD5 command to calculate a hash of this file. And this results in a unique identifier that can help us uniquely identify the set of Python dependencies defined in this requirements.txt file. And so when the Docker container runs your application, it will check to see if this hash exists in the cache in the bottom left. And if it does, great. They'll download it, unzip it, and run with it. And if it doesn't, it will create a virtual environment, do the process that may take a little bit longer where you install the packages, zip it, and then upload it to the file cache on the left, bottom left, under the hash of the content so it can find it again. And so with this approach, we solve the latency issue for slow startup times by caching the virtual environment. And we're also creating the virtual environment on the same system every time. So this handles the portability issue of virtual environments. And in summary, this setup here allows us to continue using the strategy of decoupling your Python dependencies and app from the Docker image. Okay, so let's talk about the second strategy. So Python has its own native way to package applications without relying on something like Docker. And this helps us with the overhead of managing the portability of our Python application. So PEP 441 introduces a way to package your Python application into a single .pyz file. And with this, you can run a built-in command, and it will turn your complex Python applications, your Python application, into a single file. So you can have a bunch of files in an application. The output would be one file, a PyZ file. So compared to a zip archive or a tarball, you don't need to unpack your code and define your application entry point. This handles it for you. And One challenge with this is that it does not bundle your Python dependencies. As shown in the image here, the Python code is nicely bundled, but the Python dependencies are still managed separately outside of the box around the Python dependencies or Python app. Okay, so we can take PEP 441 one step further, and this can be solved by something called a Shiv archive. So Shiv is an open source tool that was created by LinkedIn, and it does the same thing that PEP 441 does, but it also bundles your Python dependencies as well. So compared to the diagram I had on the previous slide, that Python icon is now inside the box. So they're together now. And this truly means that your application is self-contained and portable as a single file. Okay, now because we have a process to generate your Python application and dependencies into a single file, you have a distinct build process for Python applications. So let's see what this would look like at a high level. Okay, so here's a high-level overview. We utilize the PEP 441 standard with Shiv archives to build a .pyz file that have fully self-contained Python environments to run our application. And we only have to manage one single Docker file that is used for both building the application and for running the application. And this decoupling gives us flexibility, portability, and a clear convention for managing applications, more enterprise ready. It also gives us the optional bonus of being able to have something that we can consider a dedicated build process that can handle tests, running type checks, as well as running the actual process. So this is a distinct build process that the application would use. The Python dependencies are defined in the requirements.txt file on the top left. And the Python application, defined right underneath it, are passed into a Docker container that generates it into a single Shiv archive. And this gets uploaded into persistent storage. When the application runs, it launches a Docker file using the same Docker image that it was built on. All it needs to do is download the Shiv archive file and run it. And so with this approach, we bypass the issue of startup latency by having something we can have as a distinct build process. And we de-risk the portability and overhead of complex Python applications by bundling them into a single file. So in summary, I discussed how we build a Docker image for every deployment into one where we can have a single Docker image and manage our Python dependencies and Python applications separately. And this can be managed by using a simple zip file if you want to, but I covered some of the trade-offs for that. And we can go one step further. Caching virtual environments or bundling your application and Python dependencies as a PEP 441 Shiv archive. Okay, so this is summarizing everything. This is basically the last slide. So the ideas and concepts I presented today are from actual challenges that I've encountered and that I've had to solve. I don't expect these solutions to work for everyone. And that's realistic. Not everyone can copy and paste what I propose and just use it, right? But since we're all solving unique problems in our organizations, that's the reality. And my advice to everyone here as fellow engineers is that if the standard approach works for you, then go ahead and use it. But don't be afraid to question it and set up better approaches. And I hope that the presentation today provides you with some insight and perspective on how you can think differently about how you deploy your Python code, rather than just using the de facto, put everything in a Docker image type of approach. Okay, so that's my presentation today. Thank you. I know there's a lot of conference talks on the schedule, so thank you for coming here in this room. I appreciate it. Appreciate you guys coming here, wanting to hear me talk. And also just a quick thank you for the PyCon staff for putting together this event. It's definitely not easy to organize these types of events, so I really appreciate it. And yes, we will follow up with a Q&A. Just two quick things. Feel free to contact me at my email on the bottom right. If you want to connect with me on LinkedIn, it's right above my email, but please just say that you're at this PyCon talk or you're listening to this because I get a lot of spam. I don't want to decline you for some reason. And yes, if you have questions afterwards, because this was kind of complicated, you can speak to me in Chinese after the conference. I'll be outside or something, but yeah, thank you.
Yeah, thank you, Justin. We now have about 5 minutes for Q&A.
Okay. All right. Did you consider building the environment with new Python dev tools UV? I think it might increase the latency issue. It might cover the strategy you mentioned. I will say that the initial build predated some of the popularity of UV today. I have looked into UV, but yes, I think it would definitely decrease the startup latency because UV has better pip install performance. At the end of the day, if you are it's what you want, right? Like if you want to use UV and you can tolerate the latency from horizontal scaling by running UV install every single time, please go for it. My context was that we wanted maybe like 500 milliseconds startup latency, somewhere around there, right? And at that point, even if we did use UV, which runs significantly faster than pip install, it wasn't necessarily the right approach in my context. Where should the file cache be? The file cache should be something persistent outside of a Docker container because Docker containers are ephemeral. So it really is, it's where you would dump something that you would want to, right? So the most common example would just be AWS S3 or Google Cloud Bucket. Those would be the most obvious answers to that. Isn't the initial problem solved by Gitted Docker files instead of conserving the images, since the images can be generated on demand? I need to digest what this means. Essential problem solved by. Isn't the problem solved by having Gitted Docker files instead of conserving the image? I guess my interpretation of this question is like Docker files can be generated through a CI process already. It's not that much management, and you can just have some process to create them. And so, like, what's the point? I guess. At the end of the day, you're still going to have a lot of different Docker files. And I've been in organizations where everyone starts taking each other's Docker files, building on top of it. Someone leaves the organization that may have created Docker file A, and you have like 6 levels of inheritance where they're using a Docker file. And eventually they become black boxes. So yes, even if there is a process to kind of generate these, there is a state where your Docker file, Docker image becomes more or less a black box, and you work with the pieces that you know. But ultimately, if you have to go inside and you have to make some kind of update because maybe the encryption library that you have in that image is just broken, it becomes kind of complicated to glue all these things together. Can you show the benchmark between standard method and shiv method when Kubernetes deploy your code in production environment? Standard method, I guess that's the Dockerfile method and the shiv method. I will say that it's probably a factor of tens of milliseconds up to hundreds of milliseconds. And the reason for that is because the nice part of the standard method, the one that I say is the classic one, is that it downloads the Docker image, and in Kubernetes, you can more or less have your Docker images cached, so it doesn't have to pull your 14 gigabyte Docker image every single time. Versus the shiv method, you have to download a file from persistent storage like S3 every single time. And in that case, yeah, it's going to take a little bit more time. It just depends on how fast your network latency is. But we could also solve these by putting a cache layer in the actual Kubernetes cluster itself. So you're doing the same thing it does for the Docker image when that is kind of natively cached in your Kubernetes cluster. If you archive the application with shiv, all dependency files are included together, so the capacity will be very large. What is the actual capacity? This depends on your application, because some people have what I consider mega requirements files, where they have maybe like 100 files defined in a requirements.txt file. Some people are leaner with theirs. So it depends. The easiest way is just to do the example where you pip install into a virtual environment, ls.lh, and you can see the file size. And more or less, that's going to be the size. Of course, if you want to like compress this further, you can do so, but that's a real world example to get yours because it really depends on the person. We'd like to know the comparison between Docker multi-stage build, which seems to fit the dependency layers idea. Yes, so Docker multi-stage build will work pretty well. This ties back into the previous example I just kind of talked about, where Docker ends up being black boxes for a lot of people. So while it looks good on paper, in my experience, I find it creates too many black holes and black boxes where you don't know what's actually in the Docker image. Looks similar to how Nix works. Why not just use Nix? I'm not quite familiar with Nix. If you want to talk to me about it afterwards, I'd be happy to do so. Or if you want to email me and I can do a quick lookup and do a comparison through email or something, I can do that. All right. Thank you for the questions, everyone. Thank you for listening to me. I appreciate it.